In today's video, we are going to cover how to read a digital input signal using a Raspberry Pi and C++. Specifically, we'll be using the pigpio library to read the digital input signal and using a switch to generate that signal. Now, if you remember when we talked about the LED, the connections were fairly simple on the hardware. We had our GPIO pin, we had our LED, we had a resistor to limit current, and then we connected that to ground. And when we set the GPIO output to high, the LED would turn on. When we set the GPIO output to low, then the LED would be off. So you might think that connecting a digital input signal should be pretty much the same. We connect a switch to the GPIO line, we connect the other side of the switch to ground, and maybe you decide to put a resistor in place somewhere or not. But the problem we have here is that yes, while the switch is closed, when it's open, we don't really know what the voltage here would be because there's no input voltage when the switch is open. In electrical terms, this pin signal is floating. It could be 0, it could be 5, it could be somewhere in between. Because basically what it's going to be picking up is the ambient electrons in the air. And then the value here at the GPIO pin will be unknown. And if we do the same thing but switch from a ground connection to a 5-volt connection, we have the same problem. Yes, when the switch is closed, we get a solid 5 volts at the GPIO pin, but when it's open, we don't really know what value is being provided. So this means that when we read a value in the microcontroller, we don't know what we will get. It may say it's 5 volts, and we think there's a high logic. It may say that it's 0 volts, and we think it's a low logic, even though the switch is open. And what we're trying to say here with the switch open is that the potentially the switch or the input signal is false. So to alleviate this, the first reaction may be to connect a 5-volt supply directly into the GPIO pin. So we get 5 volts when the switch is open, and then put the other side of the switch to ground. So now when the switch is open, we'll get 5 volts, and then when the switch is closed, we should get ground, or 0 volts. The problem with this connection is that the current flow between the 5-volt supply and ground is going to be extremely high. We have nothing in line to limit the amount of current. And this can cause damage to your electronics. So to solve this problem, we use something called a pull-up or a pull-down resistor, where the resistor is used to limit current flow, and the direction, whether it be pull up or pull down, is based around where in the circuit the resistor is relative to the switch and the GPIO input line. So here we see a pull-up resistor where the resistor is sitting connected to the input power, 5 volts, 3.3 volts, and then that other side of the resistor is connected to your GPIO line. Then the resistor is also connected to a switch, and the switch is connected to ground. In this configuration, the resistor is being used to help pull up the GPIO pin to your 5 volt or 3.3 volt supply. Hence the name pull up resistor. So when the switch is open, the GPIO line is pulled to high. When it is closed, it will drop to 0. You can do the same thing with a pull down resistor. So here, the GPIO pin is connected to a resistor that is then connected to ground. So the resistor is pulling down the voltage to 0 volts. We have a switch connected to the resistor and the GPIO line, and that is connected to our 5 volt or 3.3 volt supply. So in this configuration, when the switch is open, the GPIO pin will read low or 0 volts, and when the switch is closed, it will read 5 volts. Notice that the selection of pull up or pull down resistor impacts the direction of the switch that will indicate a high value or low value. In a pull up resistor, when the switch is open or off, the GPIO pin will read a high voltage. And typically, high voltage is read as true in positive logic. Whereas when the switch is closed or on, the GPIO pin will read a low voltage, which will often indicate a false value. So with a pull-up resistor, on switch is going to be a low value or false, and off switch is going to be a high value or true. And that's going to be different than what you normally will think about. A pull down resistor is going to give you the configuration you're most likely expecting, which is that when the switch is off, the GPIO value is 0 volts or false, but when the switch is on, the GPIO value will be high or true. So just keep in mind that the selection of the pull down or pull up resistor is going to impact the voltage level you read at the GPIO pin and impact how you should treat that when you convert it to a Boolean true or false. Now, if you're using a microcontroller, such an Arduino or something similar, you will typically have to connect these pull up or pull down resistors yourself. The Raspberry Pi, however, already has internal pull up or pull down resistors. If we go to the Raspberry Pi documentation, we will see that it mentions that there is a default pull, meaning pull direction up or down, for the GPIOs within the Raspberry Pi. And we can figure out what that is using looking at this document, the ARM peripherals datasheet. If we go to that document, we'll see that different GPIO pins have a default pull. So if I'm using GPIO 17, then by default, that pin is pulled low. But GPIO 23, GPIO 5 by default is pulled high. And we'll see that the Raspberry Pi actually has 3 settings. You can set the direction of the pin to be pull up, you can set it to be pull down, or you can turn off the pull up or pull down resistors completely. So you don't have to connect these pull up or pull down resistors. You just need to configure the Raspberry Pi to the direction that you want. So from the wiring perspective, it's going to look more like this or this, where you're just simply connecting a switch to ground or power, because internally the Raspberry Pi has these pull up or pull down resistors. So this is what you're seeing. This part here is inside of the Raspberry Pi. And as long as you configure this connection to be a pull down resistor, your wiring of the switch to 5 volts will be correct. Now, what happens if you don't connect the connections correctly? Let's say you configure the GPIO pin to be a pull down pin, but then your wiring into the Raspberry Pi connects the switch to ground. The GPIO pin will be correctly pulled to low, 0 volts, when the switch is open, But then when we close the switch, there's not going to be any change. So in this example here, the GPIO pin is going to be stuck at low volts, 0 volts, or false. So make sure that you do configure your pin with the correct pull down resistor type based upon how you actually wired up your circuit. So now example today, we've configured GPIO pin 27 based on a pull down resistor configuration, and we've configured GPIO 17 in a pull up resistor configuration. So we've connected our switch to pin GPIO pin 27, where we specify that. The physical pin is pin 13 on the board. We initialize the GPIO library like we did last time. And then we need to configure the pull direction for that pin. So I create a little helper function here to do that, configure pull. And if we go look at that function, this is the GPIO function we need to call, where we call set pull down. And then there's a pull up direction here. GPIO set pull up down. And then there's a define that specifies the direction. So PI, PUD down, PI, PUD up, or you can turn it off completely. We get the result, and then we check to make sure that our operation successfully completed. So if you looked at my LED video, all of this would look very familiar to you. We then verify that we didn't specify a bad GPIO number, that the direction we provided is valid, or potentially there was some other unknown error that occurred. Once everything was good, we can return true, in which case then we just continue. If there was some error configuring the pull direction for the pin, we would terminate the application right away. We then need to configure the pin to be an input pin. So just like in the LED video, we configured the pin as output, we need to configure the pin as input in order to read the signal from the switch. So again, very similar, GPIO set mode. This time the mode will be input instead of output. And then we verify that we were able to correctly set the mode of the pin. Again, I create a little bit of a helper function here to eliminate some of the duplication or complexity of the main function. If we had an error configuring the pin, we would terminate the application right away. And then we just read the pin input using this GPIO read function. And if the value is less than 0, there was some error reading the GPIO pin value. If it's 0, then we assume it's a false. If it's 1, then we treat that as a true value. And all we're going to do for now is print the state of the switch to the screen. So we read the GPIO pin value. If it's high or returns a value of 1, then we're going to treat that as a logical true. We say the pin is active, or the switch is active. Then we check to see if the switch state changed from what we had it as before. If it does, then we print this new output to the screen. This code here for checking the state has changed since the last kind of iteration of the loop, is primarily to avoid spamming the screen. So this code here is only in place in order to reduce the output to the screen. It's not necessary for reading anything from the pin. The only thing you need to do for reading the pin is calling this line, verifying that there wasn't an error, and then deciding if a 1 coming out of GPIO read is a true or false based on your own logic on how you want to treat the position of the switch. So let's run this and see what happens. This is read switch 1. We need to do sudo. We're configuring the switch, and then when I toggle the switch direction, we should see some output appear on the screen. Now, one of the things you may notice is that sometimes I'm toggling the switch and multiple print lines or prints appear on the screen. It will say state active, then state not active, and then state active again. This switch specifically, or particularly, when I'm switching from the off position to the on position, there's a little bit of looseness in the switch, which causes it to trigger a couple times. And normally your switches wouldn't act this badly. I think the switch is a little bit loose, but it brings up a good thing to highlight, which is the idea of switch mechanical bounce. So when we switch from on to off, it looks like a very clean transition to us. At the electrical level, there's actually something called bounce, where the signal is going up and down for a short period of time. And when that happens, depending on the speed of your application, it may look like the switch went on, then off, then on, then off, and it could throw off your logic in your application. So you have to be careful of this mechanical bounce, and you can take different approaches in terms of how to address that. I will link to an article that talks more about debouncing your switches or your input signals. And I won't really do anything with it in today's video, but it's something that you should be aware of. It's a very common technique in software to debounce your input such that you wait a period of time before you decide, yes, the value has completely transitioned or not. So you may detect that it went high, then you may wait for some period of time, check it again, make sure it's the same value expected, and if it's true, then you will say, yep, the value is now high or low. One thing you may have noticed between the last video and this video is that there's lots of checks that we're doing to verify that the value you're reading is correct. So, or the operation we attempted to do worked successfully. If you go and look at like my configure pin function, you'll see that after I call GPIO set, I want to verify that there was no error happening with this set mode function. And what ends up happening is there's a lot of code duplication in our applications. So when you looked at Flash LED, Flash LED 1, etc. in my previous video, the code was very similar and there was lots and lots of duplication. And it was fairly complex or really dense just because there's lots of checks to ensure that what we're doing is functional. And this can become really annoying, frustrating, makes the code more difficult to read. And one of the things that people end up doing is they simply stop checking that everything is working correctly, which isn't terrible, because if it's working at one point in time, it's probably going to work later. But that's not the best practice. Ideally, you'd be doing every operation, just verifying that, hey, yes, this did work, so that you can detect errors as soon as they start occurring, instead of just assuming everything is working. In order to address that, I started creating these helper functions like configure pull, configure pin, etc. And I was putting them in my main function. Well, this makes the main function easier to read, but doesn't address the duplicate code issue. So in order to make these applications a little bit easier to understand, a little bit cleaner, I decided to create a libgpio library that I can use to encapsulate all of the functionality that I was using for these other helper functions like configure pull. So that is also shared with the code for this project. And for right now, it only has a simple LED function and switch class. So this is going to be a C++ based library that you can use to do some of the examples and that I will be using going forward. So let's walk through the libgpio library a little bit and just kind of show you how it works and how it looks. So there's a separate folder called libgpio, and inside we have a series of classes. We have a LED class, which encapsulates our LED output. We have a switch class that represents our input signal that we're dealing with today. And we have this pull direction class, which is an enumeration type class that is used by switch to configure the direction of the pull up or pull down resistor. We build this into a library using CMake, and the name of the library is going to be libgpio. This library is still using pigpio as the underlying code calls for the direct interaction with the GPIO pins, and then we still have FMT being used to help with some of the output formatting. Because this is a C++ based library, I decided to use C++ based exceptions for the error handling. So if there is an issue, then the code will throw an exception, and we will use C++ exception handling to detect the issue and cleanly handle it. So if we look at the LED and we look at what's happening class, the LED class, and see how we wrote this, when we create the LED object and we specify the GPIO pin, that is when we set the mode of that pin to be an output. We verify that we could correctly set the mode, and then if there's an error, we throw an exception, like I mentioned before. And then when we set the output, we simply call GPIO write, which doesn't return any value. So, right, the code here is going to look very similar to what we've done in the previous video. It's just now all encapsulated inside of a class, and we are throwing C++ exceptions as necessary. So when we look at this example, the flashing LED example with this new library, we see that we can simply instantiate an LED object with the pin type. Then we just say, hey, set the output of the LED to be true or false. And then this is much cleaner, much smaller application than the last set. One thing you might be curious about is, well, when does the GPIO initialize function get called? Because you'll see that we don't do that at all. We simply instantiate the LED class, and behind the scenes, GPIO initialize is happening. The way we do that is we have this base class called device that has this static private variable called mDeviceCount. And in the code, when we first instantiate the device, we check to see if the device count is 0, in which case we initialize the GPIO library, the pigpio library. This is also where we disable the pigpio signal handler, and I added in a pound define here to say you can use the built-in one if you want. You'll get that output if you don't override the signal handler, but by default we will disable the pigpio signal handler, and then we initialize it. And then the LED class inherits from device, and the switch class also inherits from device. So whichever object is first constructed, this code will get called, and the GPIO initialize will get called. Conversely, in the destructor for the device object, we check to see if mDeviceCount is 0. So when we construct, we increment the count to make sure, or count the number of devices that have been instantiated. And then when the device is destroyed, we decrement the count such that when we get to 0, there are no more objects that need the GPIO, the pigpio library. We go ahead and clean up after the pigpio library. So by doing this, we can encapsulate all of the pigpio requirements in terms of initialization and termination, and it makes our code a lot easier to read and write, because now we don't have to constantly check if something worked correctly, and we'll let C++ exceptions handle that for us, which is much safer than not checking the output all the time, which is what would most commonly happen. So we looked at the flash LED application with this new library, and if we do the same thing with the switch, this is what the switch application would look like. We simply instantiate a switch. We specify the pin we're using, which is 27. We specify that this is going to be a pull down input configuration, and then I can simply read the switch value. Yes, I should probably rename this to be input. I will do that when before this video is posted. So the new version will say get input, not get output. And that's a bug on my part. Another thing to highlight with the libgpio library is how we reference that code base within our main applications. So the libgpio library actually lives in a separate folder and has its own separate CMake list file in order to build it. But the way we're going to use it for now is we're just going to reference the library directly and let it build as part of our main application. So this keeps it simple, where when we build our main applications like Flash LED 4 or Read Switch 1, we will simply use that library, but the library itself should be configured in a way that you could build it and then reference it somewhere else. So the way we do that in CMake is we use the add subdirectory call. We say the directory that we want to add to be built is the libgpio library, which is again in this location. And because it is what CMake calls out of source, meaning it is not next to all of the other source files, we need to specify a folder that will be used to build the library. So if we go look at like our build folder, this is where all the libgpio specific build files are. And here you'll see the library that was generated, libgpio.a. Linux prefixes everything with the word lib, and then the name of the library is libgpio. That's why it's a libgpio. Once that is built, we can then reference that library in the way we were doing before using target link libraries. So I add an executable, flash LED4. I'm trying to build this file, which is my main for this application. And then I reference the name of the library, libgpio. Notice that I don't have to mention pigpio or FMT libraries anymore like we did before. And that is because libgpio references them directly and specifies that anybody who is using libgpio can or should know about the existence of pigpio and the FMT libraries. So by marking these things as public, it means that downstream applications such as Flash LED4 will be able to use them and reference them, use the includes directly, etc. So if I now run the version of the application that is using my custom libgpio library, we'll see I specify that in my little output to the screen. And then when I toggle the switch, we should see the same behavior of it saying active, not active, as I toggle the switch. So now let's look at the other switch, the one that is configured with a pull-up resistor. So that one is connected to GPIO pin 17, which is physical pin 11. Everything else looks identical from the other application. The only difference is that we need to configure this to be a pull-up because of the fact of how we've wired the pin. Now, if you remember and we look at the default pull direction of all the pins, then some are pulled high by default and some are pulled low by default. However, we can configure the pins to be whichever direction we need them to be, because GPIO pin 17 by default is low or pulled down, but we are going to pull it up. And I would recommend that it's best practice to always specify the direction of the pull, even if you're going to use the default direction. But I personally don't like to rely on the default value or rely on the hardware being in a specific state. I would rather specify explicitly this is the direction it needs to be, because you don't know what might have happened before your application ran, and it's always just safer to specify, hey, I want you to be in a pull up or pull down configuration. Even if that was your default, let's just make sure that that is what is configured. So again, the only difference between this version of the application and the previous one is that we are using a different pin, and then we are specifying it to be up. And because of that, the logic is actually different. So when the switch is on, what you will get out of is active is a false value, and when the switch is off, what you will get is a true value. So let's look at that and see what that looks like. So here we see we run the application, and the very first thing it does is prints out that the state is active, because we assume, or we start the application with a switch state of false. We checked the value here, and then we said, oh, well, it's now active, and so we should print out this value. But if we look at the actual switch position, the switch is going to be in the off position or the open position. So what that's saying is that the open position of the switch is going to be interpreted as a true value from this function. If you wanted to, you could invert the logic here in order to make it easier for you. So if you wanted to say, well, I want an on position of the switch to always mean true, but I need to use or want to use a pull up resistor, then you just can invert the logic at this point here. We'll see this a little bit more clearly in read switch 3, where we read both switch values and then we show what the values are if any one of them switches. We run read switch 3, then we'll notice that switch 1 says not active, but switch 2 says active, even though both switches are in the open or off position. And as I toggle the different switches, you'll see how they report different values. So if I switch both of them to the closed or on position, then switch 1 will say active and switch 2 will say not active. So that's how you read a digital input signal from a switch using a Raspberry Pi and the pigpio library. Going forward, I'll probably continue to expand and add to that libgpio helper library. I really like that we can keep the code more encapsulated. It'll make the applications a little bit easier, but I will continue to show what the low-level pigpio calls are. But I want to reduce the duplication and also show you some good software programming practices in terms of how to encapsulate your functionality, define classes so that you don't have to repeat code or your code is easier to read. The code that I showed today can all be accessed via a GitHub repository, which I'll link below in the video description. And then I'll also include some additional links to articles about pull up, pull down resistors and debouncing switches. The article itself is focused on hardware debouncing mechanisms, but is a really good introduction about the problem in general so that you can be more aware and get more insight. If you enjoyed today's video and want to get more content like this, please share with your friends, like the video, and subscribe to the channel. If there's a topic that you would like me to cover specifically, please let me know and I will try to cover it in a future video. That's it for now. I'll talk to you soon. Later.